Hello, good evening. Can you hear me?
Yes. Hi.
Yeah, how are you?
Fine. Thanks. And you?
Yeah, I am fine. Okay.
Good.
After a long
Great.
time, we will meet and take the class again. Okay.
Yes.
Okay, so I hope you also try to practice for the previous session. Okay. And face any problem, they'll talk about the problem solving class. So today's session, I discuss about the another new topic which is not completed yet. Okay. So let me share my screen.
Yes.
Can you see my screen?
Yes. Now yes.
Okay, so let's start. Just a minute. Let me open my slide. Okay. So today's session I discuss about that SAR image processing, mainly Sentinel-1 and Sentinel-3 for submarine vegetation monitoring and time series analysis, how we can easily do. As well as I also try to add another topic which mainly called the bathymetry, how we can easily monitor the bathymetry, and then also talk about that mainly Sentinel-3 imagery, and we calculated the chlorophyll, basically harmful algae bloom, and also water turbidity and water clarity. We also discuss about this type of topic. So let's go, we'll start from beginners. Yeah. So basically there are a lot of importance for submarine vegetation, seagrass or clive, this type of things, and they are the vital role in our biodiversity or erosion prevention, and also blue carbon. They are the vital role for the submarine vegetation. Different types of vegetation such as seagrass or grass bed or cliff, and we can easily use the remote sensing, large scale monitoring. We can easily take the big study area for the whole submarine area, and then we can easily monitor the vegetation and also compare the vegetation for the different time period using the different types of satellite sensor. And we also use the monitored submarine vegetation change over time using Sentinel-1 SAR data. It's a SAR data, as well as we also use the Sentinel-3 for optical or ocean color. This is the another sensor we also use. And we also try to develop the time series analysis for the trend detection. And we are use this type of sensor. You can see for the Sentinel-1, it's a SAR data. Basically, SAR data, we find out the C-band radar, dual polarization VV and VS band, and it also cloud penetrating, okay, and also sensitive to surface roughness. And also Sentinel-3, basically it's the ocean color, and from the ocean color we can easily monitor the chlorophyll A and also turbidity. We can easily monitor, and from the Sentinel-3 we can easily identify for sea surface temperature. Okay, so let's go try to I will show you that all of process step by step, then you are able to do this type of analysis. And basically vegetation proxy indicator we also use using the Sentinel SAR imagery. So basically for the SAR indicator, VV and VS ratio, if it will be high, it mainly more roughness or vegetation density is also high. And temporal smoothing, it's the 3-month median we also use for that. And optical indicators, basically chlorophyll, it's basically chlorophyll indicate the healthy vegetation. Okay, if the chlorophyll is high, then we can easily find out the healthy vegetation. And sea surface temperature drop and high chlorophyll, it's equal to algal bloom. We also identify using the sea surface temperature and high chlorophyll. These two things when you combine, then we can easily identify for algal bloom, easily detect from the satellite imagery. And also it's also some limitation such as basically SAR cannot penetrate deep water. Okay, basically greater than 15 meter. Okay, cannot penetrate greater than 15-meter depth. And submerged vegetation single is weak compared to land. Okay, and records the validation with in situ data or high resolution data we need. So this type of limitation you also find out when you try to use the Sentinel-1 SAR data. Basically SAR cannot penetrate deep water. Okay, greater than 15 meter, it cannot penetrate. And then submerged vegetation is single is weak compared to the land and requires the validation with in situ data or high resolution data. And radar vegetation index, so it's one kind of index, it's called the RVI, basically radar vegetation index. So this index is useful to identify for vegetation using SAR data, especially like Sentinel-1 SAR data. It is designed to assess the vegetation structure, density, and also growth without relying on optical data. Okay, and which can be affected by cloud. Optical data basically for the Landsat, Sentinel-2. So this type of data set we find out lot of cloud. But when you work with Sentinel-1 data, Sentinel-1 SAR data, then this type of cloud is not affected in our result. So that's why radar vegetation is very important for the cloudy region, such as submarine or marine. Okay, so this type of coastal area or coastal or sea surface. So this type of place we can get the more better result than optical data, because optical data is affected by cloud, but SAR data is not affected by cloud. Okay, we can easily find out more better vegetation analysis when you work with the cloudy region. And RVI, it's one kind of radar vegetation index we can easily use using Sentinel-1 SAR data. And you can see this is the one kind of example for the radar vegetation index using Google Earth Engine. I'll also check my result for my mangrove forest. So basically high positive value indicating about that high dense vegetation, low positive value indicating about the low dense vegetation. So it's one kind of radar vegetation index map. And if you check it, this is the formula about that radar vegetation index. So this formula basically 4 multiply with VI band divided by VB plus VI band. So when you compute this equation, then we can easily generate this type of radar vegetation index map, and we can easily identify for vegetation, and it help you to penetrate with the cloud, because radar imagery cannot affected by cloud, but optical imagery such as Landsat or Sentinel, so this type of imagery is affected by cloud. So that's why it's very important when you work with radar satellite imagery, we can easily get the vegetation analysis in the submarine region or coastal area or sea surface. We can easily detect this type of vegetation. Okay, so this is the formula, you can say RVI. So this formula when you compute it, then we can easily find out the radar vegetation index and compute the vegetation. And if you can see the basically this is the feature. So basically detect and monitor the vegetation using SAR backscatter value we also use. And data source basically dual polarization SAR data for Sentinel-1 SAR data VV and VIs. And value range basically 0 to 1 we find out. And high RVI value, it indicates the dense or complex vegetation such as forest or crop. Okay, when you find out the high value of radar vegetation index value, if high, then we find out the indicate the dense vegetation or complex vegetation. And low radar vegetation index value, it indicating about the bare soil, water or sparse vegetation. Okay, this is the value range about that. And you can see we already know about that one index. It's called the NDVI. We already use using the optical data, Landsat or Sentinel. We already use this type of optical data and already calculated the normalized difference vegetation index. Okay, you already know about that, how we can easily calculate the NDVI using Landsat or Sentinel imagery. So why use the RVI instead of the NDVI? Basically needs optical data. When you calculate the NDVI, you need the optical data such as Landsat or Sentinel imagery. But when you apply the RVI, it work in all weather condition. Okay, day or night, it work on in all weather condition. And NDVI is affected by cloud or shadow. NDVI is affected by cloud or shadow, but RVI not affected by cloud cover. Okay, when you use the RVI, it not affected by cloud cover, and it based on reflectance red and near infrared band. And also RVI basically based on the radar backscatter value, VV and VS value. So this is the common difference between the RVI and NDVI. And there's a lot of use of RVI index, such as monitor the submerged or aquatic vegetation. When you work with aquatic vegetation, then we are also use the RVI. It provide you the more better result. And assessing the crop health or forest biomass, tracking the flooded vegetation. It's very important. When you tracking the flooded vegetation, you can easily use the RVI and tracking the flooded vegetation. And also wetland change, we also use the RVI. And completing the NDVI in cloudy and tropical region, we also use. Okay, suppose cloudy region or tropical regions, when you work, then you try to use the RVI and also get the more better vegetation analysis. Okay, so this is the one thing. So I will try to explain about this RVI, then move to the next slide for the SAR. So let's go. Okay, just let me open my code. Okay, so in this case, okay, just let me show you that data source. So in this case, we try to use this data. So this data, just I simply open. It's a Sentinel SAR data, C-band synthetic aperture radar data, and we can easily find out. You can see this type of dual polarization, 10-meter resolution, VV and VS band. We can easily find out single copolarization or dual band cross polarization. Okay, so this type of band we also use in here, and then further we try to calculate. So first step, we need to define our study area and also define the date range. So here I just simply import my study area. Okay, it can be anything, your shapefile or anything, you can simply import. And you already completed my 7 days online training program, so that's, you already know about that, how we can easily upload our own shapefile and further we make the analysis. So you already know about that, this thing. So in this time I simply skip this part. Okay, so here I import my study area. So this is my mangrove forest boundary in the near to the coast. Okay, so just I simply import, and then further I simply load my Sentinel SAR data. Okay, so in this case, this is my image collection of Sentinel SAR data. Just we try to filter. So how we can easily filter? So in this case, we are simply filter according our study area ROI. ROI is stored at my shapefile boundary ROI. Then filter date. So basically in this time, I simply put my time period. Okay, I take that 1 year 2022, and instrument IW, and transmit receiver polarization, I set that VV and VS. Both of them I try to take VV and VS, because in my equation, if you check this equation, this equation is the combined VV and VS band. Okay, so if in our slide you can check the equation, we need to work with the two VV and VS. Okay, both of band we need to take. So for that I simply take this, the transmitter receiver polarization for VV and VS, both of band we try to take. And then orbiting pass, I put the descending. Okay, and then select the two band VV and VS band. So now it stored the band. If you check how much image is available in here, just try to print, and then S1 is stored this full image collection. If I just print and then just use a dot size function, so now it computing how much images are available. You find out. So you find out, you can see 83 image collection. You find out in here 83. Okay, so this 83 image I want to use further and try to compute the radar vegetation index. Okay, so let's go. So now we calculate. This is the formula you can see. So in this case, I just create a function. Okay, so just create a function, and this is the formula. So just create a function. In this function, we try to compute our equation. This is the equation. 4 multiply with Vs divided by Vv plus Vs, these two band. Okay, just I apply the expression. We already know about the, what is the expression. You already complete the 7 days online training program. You already know about that, how we can easily create a function, how we can easily create the expression. Okay, it's the basic things about that. And then you simply put in here, this is the formula about that, and we simply select what is the Vs. Vs mainly it's come from the image, and select the Vs band. And Vv, what is the Vv? It's come from the image. So this is the function. This function we simply connect with our image collection. We already create the image collection. Total 83 image collection we have. Okay, we already calculate the image collection 83. So this 83 image collection, just I simply connect, because this 83 image collection is stored in the S1 variable. Okay, S1 variable is stored. So I simply connect using the map function. Okay, so this is the function. This function I connect using map function with my image collection S1. So now if I just check, suppose if I just print this with RVI, so now all of image is stored in a new band. This band name is that RVI. You can see it create this image collection, and all of images it is stored in a new band. This band name is that RVI. Just check it from the feature. You can see that the total 83 images, This 83 images, just simply check what is the band. We can find out the RVI. So this new band we created, okay, this new band we created. So for that, this band we also use and create the time series chart and also visualize the map of RVI. Okay, so let's go. We try to create the, okay, so in this case we try to calculate the monthly median RVI composite. Suppose I create the monthly, so that's why if you want you can also create the normal temporal resolution, there is no problem. Or if you want you can also check for the monthly, and same process. Okay, for the monthly we need to create the another function. Okay, suppose when you work with the monthly, we need to create this date range, month range, you can see. So for that we simply create a list, ee.list sequence. Okay, I put here the 1 and 12, 1 mainly January, 12 mainly December. Okay, I want to create the monthly time series chart from January to December. Okay, for the year of 2020. Okay, monthly. So for that we just create the sequence look like that, and then we create a image collection, monthly image collection for year of 2020, and then we filter and select. So now if I just print, suppose if I print that RVI monthly, this variable, so then we find out that only for the 12, okay, for that 2020 we find out. So you can see the 12, okay, because I need the data for year of 2022 whole month. Suppose January to December, whole month I need the data, whole month I need the data. So for that I simply put here, you can see image collection. When I just put here the 1 to 12, mainly January to December, then I can find out for 2020. So I can put any date in here. Okay, so in this case I show you the result for 2022. So then we find out this type of year map for 2022, this type of time series chart. So you can put any time period in here, it's also okay, there is no problem. And you can see we find out the 12. Okay, 12 basically for 2022 whole, all of month, January to December, all of month we create the collection, because I want to make the monthly time series chart. Okay, so you can create this type of things. Further we try to visualize this type of things. You can see just add the visualization, and then we just try to do this type of things, and then we can find out this type of map. When I add the layer, we can find out this type of map. Okay, so basically this type of green color indicating about the high dense vegetation, then this type of black color other things. Okay, there is barren lands, you can see this is the barren land other things. So you can also get the more better result when you are stressing it. Just I click, and then suppose I just keep stressing 90%, and you can see this is the, we put here this type of things. So high values indicating about that vegetation, and vegetation show as a green color we put in here, this type of green color we put in here. Or if you want you can simply put the stressing. Suppose I put the 98%, I think it look more better. And this type of black color indicating about the no vegetation, it can be water body or others. Okay, not vegetation. Just I apply. Or run it. Okay, so now I think this visualization is more better. So we find out the dense vegetation show as a green color. Okay, and others show as a black color or a yellow color. So it's not more dense vegetation, it's as a sparse vegetation or not much dense vegetation. We find out this type of place have the dense vegetation, but you can see this type of river, it's a river, water body, other things. So you can also change the color combination also from here. Suppose if I just put here the color, suppose I put here the color blue color for that. Okay, then I put here suppose this type of yellow color. Okay, then I put the another color, suppose this type of red color I choose. Then I choose here suppose this type of green color, and also put here this type of deep green color I also choose in here, and then I apply. So now we can also put the different types of color, and if you want you can also just export the result and also get the more better. So here you can see now it look more better. So you find out the water body, this type of water body show as a blue color, we can easily find out. And dense vegetation, where we find out the more dense vegetation, we find out the deep green color. So this type of deep green color indicating about the deep or dense vegetation. Okay, but it also have some sparse vegetation also have. Okay, but this type of green color indicating about the dense vegetation. Okay, and you can see this type of place there is no vegetation, show as a red color, and also blue color there is no vegetation, show as a this type of blue color. And you can see this type of place green color, so it's indicating about the vegetation. Okay, so further you just try to export this type of map, and also you can work with the ArcMap or QGIS software to pre-process your map. And it's very helpful when you work with cloudy region such as submarine or coastal, so it's very useful to identify for vegetation. Okay, so this is the result. So now I want to check about the time series chart about that. Oh, okay, so let's go for the time series chart. Okay, suppose you want to check the time series chart for a specific point. Okay, so for that, if you want, you can simply create a point. So here you can say I already create a point in here, so you can simply drag for any place and check the result for this specific point. Suppose I just put the drag it in here. I want to check for this place what is the scenario, month of January to December, all of month in year of 2022. Okay, so for that you can say I just define my point. So this point I want to make the time series chart. So for that I simply put the point, and then just I create the write the code in here. You can see, so we put here UI chart image.series image collection, basically monthly image collection. I already make the monthly image collection. Okay, so you can say RVI monthly. So this is my image collection. I already make the 12 month, basically January December in year of 2022. If you need the result for 2023 or 24 or 2020, just simply change the time, then we can easily get the result for any specific year, all of month time series chart. So now point, this is my study area. I simply put, and I want to calculate for average. Okay, average RVI value, and then scale measure 10 meter. So VV and VS band resolution is the 10 meter, and then we put the title, look like that. This is the title, you can put any title, no problem. And line width or point size, you can say also put this type of point size. Okay, and further run the code, then we can easily get this time series chart. So this is the way to create the time series chart for RVI, and we can check which month provide you that high vegetation or dense vegetation. We can easily check it from here. So in this time you can see for this time we get this type of things. Okay, so you can see this, it show the low. Okay, June, okay, month of June we find out the low vegetation, but you can see in the December we find out that high vegetation index for the RVI for this point, for this specific point. Okay, so due to the different region behind, such as for precipitation or rainfall. So further you also try to make the correlation, why we find out the high vegetation in the month of December, why we find out the low vegetation in the month of June. So this type of things, further you try to correlation using the different types of climatic factor and also check the result. Okay, so this is the one way, but this is the way we try to apply. And further we try to check the vegetation in the coastal area, okay, or any place where there are the lot of cloudy region or submarine region, we try to apply. Okay, okay, so any question please?
No, at the moment it looks like it's easily to implement.
Okay. So you also try to
Thank you.
implement this type of things for your study area. And further face any problem, we have the problem solving. You can get the lifetime problem solving solution. Okay, after completing this training, when you face any problem regarding this topic, you can get the solution anytime, inshallah, no problem.
Yes, thank you, Mihan.
Okay, so this is the one way we discuss. So RVI, so it's called the radar vegetation index. We can easily apply it where we find out the lot of cloudy region. We can easily apply the radar vegetation index, and we can easily get the more better vegetation map or vegetation analysis. Okay, so let's go and next topic. Okay, so it's very important how we can easily detect the ship using Sentinel-1 SAR data. So we can easily find out a lot of ship in the near to the coast, and I want to detect this type of ship. We can see this type of ship, as well as we can also count how much ship in here for the any specific coastal area. Okay, so then we can easily use the Sentinel-1 SAR data, and further we try to detect the ship using Sentinel-1 SAR data. So let's go, we try to discuss about that, how we can easily detect the shape using Sentinel-1 SAR data. It's not. Okay. So let's go try to discuss about that. So this is the one kind of region. Okay, I think this region in near to the Singapore port. Yeah, yeah. So now in this case, if you check the imagery, so this is the Sentinel-1 imagery. So if you just simply filter, so just I simply draw the study area look like that. So this is study area or this coastal area I want to detect for the ship. Okay, using the Sentinel-1 SAR data. Okay, so you can see this is my shape file, or you can easily draw your study area where you want to just need the result. So I put it, and then I can just get this type of imagery. So if you check it, in this case I just use here the VV band. Okay, VV band I just use, and then we can easily just have stressing source 98%, then check what types of finding, just apply. So now you can see we can find out this type of imagery. Okay, just I display only for the one band VV, because it reflects this type of ship or boat easily. And others you can see water body show as a black color. Okay, but this type of boat or ship show as this type of white color pixel. You find out, you can see. Okay, this type of white color pixel you find out in here. But normal water body show as a black color. Okay, because it's not reflect with this PV band or VS band, it's not reflect. So you find out this type of imagery, and after that if I just check for the ship, so you can see this type of red color. Okay, if I just remove, you can see this type of red color indicating about the ship. Okay, when I just ship marks mainly I just identify only for ship, and I remove the water body pixel. All of water body pixel I simply remove from my imagery, just I marks only for the ship. So then we can easily find out this type of red color, it's indicating about the ship. Okay, and further if I just ship polygon, suppose this type of things, I simply create a polygon. Okay, just check the polygon. So then we can find out this type of polygon. Okay, so it's a vector data. So now this type of ship work as a polygon, you can see it's a polygon. So further this polygon you simply export as a shape file or KML file or KMZ file, and then further you can also use the map and also make that different types of analysis. Okay, so you can see first step, I just simply import my image. This is my Sentinel-1 imagery. So from this image I just remove this type of water pixel. I don't need the water pixel, I just need only for this type of white color pixel who is indicating about that ship. So if I just marks ship marks, then we find out this type of result for the ship marks. Okay, and then this type of ship marks, it's a raster imagery. So this raster imagery I convert as a polygon. So then we find out this type of vector or polygon. Okay, so this is the result. So now how I can do it, I will show you that. And you can see how much ship I find out. Okay, I also calculate the number, total ship number 255. Okay, we find out the total 255 ship polygon. We find out the total 255 polygon in this region. 255, it detect this type of blue color, indicating about the ship. And what's the total ship? We find out the total 255 ship in our study area. Okay, so let's go how I can create this type of things. I will explain one by one. So in this case we also use here the Sentinel-1 SAR data. This is a SAR data, and in this case we are just work only for the one band VV. Okay, transmitter receiver polarization we choose only for VV band, not VIS band, just only for the VV band, because VV band is reflectance more better for this type of object. Okay, such as boat or ship. Okay, it more better reflect this type of object, and also water body show as a black color. So that's why you can easily use the VV. and transmitter receiver polarization we also use in here. So you find out this type of result. Okay, so just use the only for the one band VV band. And transmit mode IW I put the time period. You can see you can also make the change analysis for the shape. Previous time how much shape, now how much shape increasing or decreasing. So this type of analysis you can also do. So in this case I just put year of 2023 1st January from suppose I choose the data for only for the 1 month. Okay, January, month of January, and filter bounds with my study area. Okay, so now from here I just take the only for the first image. So if you check how much image in here for the month of January, just use at the print and call the Sentinel-1, just copy and use at the size function. And now check how much image we find out for my study area in month of January 2023. We find out the 8 images. Okay, so now from these 8 images I just choose only for the first image. Okay, in this case you can see I don't create the median, I don't create the mosaic. Okay, just I take the single image. Suppose from the first you can also check the time period. Suppose if you just print this variable Sentinel-1, just print and run it. So now you can easily find out the all of image date. You can see total 8 images we find out from a study area, and you can see the result. Okay, just all of image date. You can see acquisition date 2023 3rd January. Okay, so this is 3rd January. Then you can see the 4th January, 10th January, 15 January. Okay, 16 January, then it's a 22 January. Okay, then 27 January. So in this case, suppose I want to work for the first image. Okay, I want to work with this imagery. So for that I simply put here the first. Okay, first mainly from this list I have total 8 images, but I just take only for the first image. So just put here the first. Okay, and clip with your study area. But if you want, you can also work with other imagery also. Just simply copy this ID. Suppose I want to work with this imagery, just copy this ID. Just suppose I just copy this ID and then paste in here. Just I will show you that how it will work. Just take a variable, suppose image, and user ee dot image and then paste here. Okay, paste the ID. Okay, just paste the ID and then further just clip with our study area. Just clip with our study area which is geometry, and then just comment. Okay, just comment this line. So now we find out the result in year of 2020 5th January. Okay, so this is the image for the 5th January. You can see this is the image for 5th January, and how much vote we find out in the 5th January. You can also compare the result. So we find out the 210. Okay, 210 both ship we find out in this time. You can see 2023 5th January. Okay, so you can also choose your own imagery. Okay, suppose which date you want to filter, just simply copy the ID and paste and also work with that. There is no problem. Okay, so now after selecting the image, so now we find out this type of imagery. Okay, so now from this imagery we just ship marks. Okay, so now image calibrated we also need. So for the calibration, for the image calibration, just I call the image and select the VB band and multiply with this variable for the image calibration. Just simply multiply with this, and after that we just simply remove the speckle filtering. So for that, in this case, for speckle filtering we just call the image calibrated, these things, focal median we use, and put the 15 circle and meters, unit is the meters for speckle filtering, and then just use the threshold. It's very important for the threshold value. So in this case you also check the some random value. Okay, suppose if I just zoom it and check the some value from here. Suppose if I just click on the inspector tab and click on here, so now here you can see you find out this type of value look like that. Okay, or you can also check, suppose this type of lower, just click on here, this type of white pixel. Okay, low white pixel. So you find out this type of value 0.0051, or you can also just click on here, you can get this type of value. As well as you already know about the outshoe method. Okay, we already know about the outshoe method. So you just apply the outshoe method and identify. Outshoe method basically it's one kind of way to differentiate two objects. Suppose in this time, in this imagery, I have total two objects. One object is the ship, another object is for water body. Okay, so now I want to apply the outshoe method, and then I just simply filter. Okay, I want to filter for, I want to separate ship and water. Okay, but in this case I just put the randomly. Suppose you can see, if I just click on here, I can get this type of value. Or you can just choose a small ship. Suppose you can see it's very small pixel value. You can also zoom it. Suppose I just simply click on here, so I find out this type of value. So just I use this value and I take greater than. Okay, speckle filter greater than, I take this value greater than. Suppose if I just copy this value and then paste here, just paste here, and then I take the all of greater than. Okay, from all of value greater than, I just use it ship marks. Okay, so now further if you run the code, then you can easily find out that ship marks result. Just run the code. But it's not the proper way to identify, because when we apply this type of things, we mistake some ship. Okay, because some reflectance value it not across the limit. Okay, so that's why it better to use the outshoe method and identify for all of ship. In this time you can see, when I put the random value, some ship is missing. You can see this shape, it not marks. Okay, you can see this type is it not marks. Okay, but when we apply the outshoe method, then we can easily differentiate, we can easily separate. Okay, so that's why it's not used the better way. So you try to identify using the outshoe method. Okay, so you also try apply the outshoe. We already know about that, how we can easily apply the outshoe. Previous 7 days class I also discuss about that. And try to differentiate. In this time we differentiate for only water body. So if I just remove all of pixel of water body, then I can easily find out the ship. Okay, so that's why you try to apply for outshoe in this code, and then try to identify for threshold value, and then we just use the greater than of this threshold value, then we can easily detect all of ship and also count how much ship we find out in here. So in this case you can see, if I just use this threshold value, then we find out the only for the 60 ship it's detected, other ship is not detected, because it in this time it's not the proper way. Some pixel value is not across the limit, so that's why it's not considered as a ship. Okay, but this type of small pixel is also considered as a ship. So this problem how we can easily solve, we need to apply the outshoe, and using the outshoe we need to differentiate water body and ship. Then I hope it will work, there is no problem. Okay, so now we compute. Okay, so how much ship in here? So we find out, suppose in this case this type of blue color, it's indicating about the ship. Okay, so now I compute how much blue color polygon in my area I want to calculate. Okay, so for that we are just use the ship polygons, take a variable and call the ship marks and apply the self marks. So if you just check it, the ship polygons, so now we find out this type of blue color. Okay, this type of blue color is indicating about the ship. So now I want to count. So further these things I want to compute. Okay, so you can see ship marks is a raster imagery. This type of red color, it's a raster. So these things I need to convert into polygon. We need to convert into polygon. So let's go try to convert into polygon. So for the polygon, we need to apply a function reduce to vectors. This function help you to convert raster to polygon. So just I simply put here reduce to vectors, and I put the geometry type as a polygon. I want to convert the polygon, and I want to convert every polygon. So every is all of pixel, red color pixel, I want to convert as a polygon. So put here the ee dot reduce or count every. Scale is the 10 meter. So then we can find out this type of blue color. Just I open it, it work as a polygon. It's work as a polygon. This type of polygon we find out. Okay, it's a ship. So after converting raster to polygon, then we need to just count how much polygon we have. Okay, so let's try to count it. So for the ship count, just use the size function. We already know about that. So just call the ship polygons and use here the size. Basically size is computing how much feature or how much collection. Okay, so just we simply put the size function and print it. So now we find out that how much ship 60. Okay, so this is the way to identify for ship. And this type of file, suppose this type of layer, you can easily download, okay, as a GOT file format, or easily download the shape file. You already know about that, how we can easily download the shape file from here. Just apply the same code and you can easily download this type of polygon. And further you can also make the map using ArcMap or QGIS software. But this is the way to compute how much shape in your any coastal area or submarine area we can easily detect using this way. Okay, okay, so any question?
No, but this is one factor that could explain the connectivity or the fragmentation. It's interesting.
Okay,
I like it.
okay,
Thank you.
okay. So you also use this type of, I'll send you all of code, you also try to use, and further face any problems to discuss about that, no problem. Okay. So now let's go to next slide. Okay, okay, so let's go. So now we talk about the sea floor bathymetry, mainly underwater topography using remote sensing. How we can easily detect the underwater topography using remote sensing. There are the lot of process. Okay, already lot of paper is published regarding this topic for the underwater topography or sea floor bathymetric using remote sensing. We also use. So I try to explain some method and also show you the practical example. You also try to use this type of things, then I also get the result for the seafloor bathymetry. So basically there are the lot of satellite imagery we also use. This type of Landsat or Sentinel-2, okay, this type of optical satellite imagery we also use. And this satellite rely on the light at iconic in water, especially in the blue and green bands, to estimate the depth. Okay, so basically blue band and green bands to estimate the depth, and clear shallow water allows blue and green light to penetrate. The deeper the water, less reflectance is recorded those bands, and also use the empirical or physical based model to estimate the depth. Okay, I also use this type of Landsat 8, 9 or Landsat 2. Basically 30-meter resolution blue and green band is helpful to identify for topography, okay, bathymetry topography. And also 10-meter resolution better for detailed bathymetry, Sentinel-2. And there are the lot of method you can see. So in this game there are the total 3 method for identify topography bathymetry. So one method is the stumps ratio model. Okay, so this is the one kind of model. It also useful to identify bathymetry in the coastal area. Use the log ratio of blue and green bands. Okay, so this is the one kind of formula we also further discuss. Use of log ratio of blue and green band, then we can easily detect the bathymetry. This is the one method, it's called the Lizinga method. Use multiple band and regression. Okay, so we also use the regression. Basically when you apply the regression, you must need the ground truth data. Okay, so when you apply it method, we need the ground truth data. Suppose some bathymetry height for the coastal area, ground truth data we need. But For the stamps ratio model, we don't need the ground truth data. We can easily use the log ratio of blue and green band. Then we can easily monitor the stamps ratio. And also you can see the machine learning method can be trained on the field measure depth data. So for the machine learning method, we also need the ground truth data also we need. And also limited uses Sentinel SAR data we also use. And this type of things, this type of model, we are just only use optical data. Basically is Landsat, Sentinel-2, this type of data. But Sentinel-1 is also used, but it's not suitable for direct bathymetry. Okay, basically SAR imagery surface roughness, not directly water depth. Okay, so this is the SAR imagery limitation. SAR imagery only measures the surface roughness, not directly water depth. It not be calculated, and can be used the indirectly. We can also use, suppose indirectly we can use, such as mapping the sea floor feature affecting the surface wave pattern, and identifying the tidal floods and also shallow reefs, and also submerge the sandbanks when water is calm and shallow. But for that, Sentinel-1 is not directly measured. It's not suitable for direct bathymetry. So further we also use it at the Landsat or Sentinel-2. It will more better. So you can see the bathymetry. So for the bathymetry, we also use one kind of band combination to identify for bathymetry. Okay, so this bathymetry band combination is that 431, basically red, green, and also coastal band. One is the coastal band. It bands to peak into water, and the coastal band is useful in coastal bathymetric and aerosol studies because it reflects the blue and violet. And this band combination is good for estimating the suspended sediment in water. So you can just take the Landsat imagery or Sentinel imagery and then apply this band combination. Then we can easily detect the bathymetry. Okay, it's one kind of visualization. Okay, just like a band combination, you can also apply and also get this type of result. So let's go. I will explain fast this type of things. Suppose, just a minute. Okay, suppose you can see this is the one kind of study area. I simply choose the submarine area. So this area we try to identify for bathymetry. Okay, and we get this type of result. So in this just it's one kind of your visual band combination. Okay, just you can see the red, green, and coastal band when we apply, and suppose it's tracing suppose 98%. Just apply. So now you can easily find out this type of sediment of water. You can see this type of place we find out a lot of sediment. Okay, but you can see this type of place, it's just a clean water, not much more sediment. Okay, and this band combination is also helpful to identify for sediment. Okay, you can see it's the sediment. This type of coastal water we find out a lot of sediment, but this type of place it not much sediment. You also get, suppose if I just increasing this place study area and run the code. Okay, I think that is not image. Okay, let me just, okay, so this is the Landsat 8 satellite image we try to use in here, and I take suppose median composite, median, and I filter suppose cloud cover, filter metadata I choose, and I put here cloud cover less than suppose 1. Okay, sometime less than 1 is not available for the coastal area because all time they are happening for that cloud formation. Let me check what's happened just on the code. Okay, it also worked. We find out it looked like that in the coastal area. We try to add the band combination. Which band combination help you to identify for bathymetric topography? Okay, basically red, green, and coastal aerosol band. B1 band is the coastal aerosol band. Just a stressing 98%, and then apply. So now we can easily identify. You can see we find out this type of place, lot of sediment. Okay, we can easily detect it's a sediment. Okay, but this type of ocean, you can see this type of place, not much sediment. Okay. So it's one kind of visualization, it also help you. But from here we cannot calculate the bathymetry height, it's not possible to calculate, it's just a band combination. If I click, I can get the band value, you can see I can get this type of value. Okay, but when you calculate the bathymetry height, this type of things, then we need to apply this type of model. Okay, we already discussed about these three model. You can see this is the one model for the distance ratio model, then Legendre method, and also machine learning. These two method, when you apply, we need the ground truth data. But when we apply this model, stamps ratio model, we don't need the ground truth data. But when you check the validation, suppose I want to check what is the validation, what is the accuracy of my bathymetry map, then we need it. But for this two method, when you apply, you must need the ground truth data. But these things you can apply without ground truth data, but when you check the accuracy, then you must need the ground truth data. So let's go and try to explain about this model. And this model basically use log ratio of blue and green band. Log ratio, blue and green band. So just we try to apply this formula and check what happened. So let's go. Okay, let me check the result first.